So we are continuing with our topic called chemical equilibria. And we are yet to look at an important law in chemical equilibrium, which we call the law of mass action. If you don't call it the law of mass action, you can call it the equilibrium law. Don't call it the law of mass action. You can call it the equilibrium law. And since I've already defined it, what we call a heterogeneous equilibrium and a homogeneous equilibrium, for this law, we are going to consider what we call a homogeneous equilibrium, in which both reactants and products are in the same phase. Let's consider an equilibrium reaction between A and B. Since we are dealing with chemical equilibrium, the reaction is reversible to form C and D. I'm ignoring the state symbols because the equilibrium is homogeneous. Let me assume W moles of A react with X moles of B to form Y moles of C and Z moles of D. If this reaction is occurring at a constant temperature, if I make it occur at any given constant temperature, then the product of the molar concentration of X, of C, the product, one of the products, power its number of moles Y, times the product of D, molar concentration of D, power the number of moles of D, divided by the product of the molar concentration of A and the molar concentration of B, each powered by the number of moles of the reactants in the equation, should be a constant. Should be a constant so long as the temperature is also constant and the equilibrium is homogeneous. This constant is equal to what we call Kc.
I beg your pardon.
Where exactly?
There on what you have been calculating. This on C power Y.
Okay. I'm saying I'm considering a homogeneous equilibrium. And in the homogeneous equilibrium, we have reactants A and B forming products C and D. If to balance the equation, I need W moles of A and X moles of B to give me Y moles of C and Z moles of D. Then at any given temperature during this equilibrium reaction that is reversible, you'll find that if I multiply the products of the molar concentration, this square bracket stands for what we call molar concentrations at equilibrium. Molar concentration at equilibrium. That's what the square brackets mean, and you should always be using them, not this the color ones. So the product of the molar concentrations of the products, the product of the molar concentrations of the products, C and D, raised to their appropriate powers, which are here in the equation, Y and Z, respectively, divided by the product of the molar concentrations of the reactants, A and B, each of them powered by the number of moles as per the equation. That value you get should always be a constant. And that constant is what we call Kc. So this is the mathematical expression of the law of mass action, or the equilibrium law. But what is that law in a statement? If I'm to give it in a statement, I will say the law of mass action states that, what to make emphasis here, the law of mass action states that if a reversible reaction is allowed to reach equilibrium at a particular temperature, the product of the molar concentrations of the products, the product of the molar concentrations of the products raised to their appropriate powers, divided by the product of the molar concentrations of the reactants raised to their appropriate powers, is a constant. What have I just said? I've just said that the law of mass action or the equilibrium law states that if a reversible reaction, the reaction must be reversible, is allowed to reach equilibrium, under what condition? At a particular temperature. Then what happens? The product of the molar concentrations of the reactants, of the products, raised to their appropriate powers divided by the product of the molar concentrations of the reactants raised to their appropriate powers is a constant. So, Abud, are you getting me?
Yes.
That's what we call the law of mass action. So, kind of reversible reaction. Each reaction is allowed to reach equilibrium at a particular temperature. Product of the molar concentrations of the products raised to the appropriate powers divided by the product of the molar concentration of the reactants raised to the appropriate powers is a constant, which constant shall call Kc, or even later shall call it Kp. If that statement is so long for you, you can state it this way. You can say the law of mass action or the equilibrium law states that in a reversible system, there is a fixed relationship. There is a fixed relationship at a given temperature. You know, students want short things. So you could go for this one. There is a fixed relationship at a given temperature between the molar concentrations of the products and those of the reactants in the equilibrium mixture. However, personally, I would prefer the first option. Personally, I would prefer the first option. Now, you've heard me talking about Kp and Kc. Kc is called the equilibrium concentration equilibrium constant. It's called the concentration equilibrium constant. So chemical equilibrium constants can be denoted by either Kp or Kc. So when you hear of Kc, then it's what is the equilibrium constant in terms of concentration, where we are dealing with the molar concentrations. Just as we have stated in our law here, if the equilibrium constant is written in terms of molar concentrations, then it is Kc. If it's written in terms of partial pressures, as we shall see later, then it is Kp. What is Kc? In other words, what is the concentration equilibrium constant by definition? We just get it from this expression here. We shall say the concentration equilibrium constant is the ratio of the product of the molar concentrations of the products raised to the appropriate powers to the product of the molar concentrations of the reactants raised to their appropriate powers in a stoichiometric equation of a reversible reaction at a given temperature. Okay? We have just said Kc is concentration of C power Y, concentration of D power Z, concentration of A power W, concentration of B power X. Where have we got Y, Z, W, and X from a stoichiometric equation? What do the square brackets denote? Molar concentrations. They are products of the molar concentrations raised to those powers there. Under what condition did we say Kc is measured? At a constant temperature. So all those concepts should be brought out in your definition. So what will you say? The concentration equilibrium constant is the ratio of the product of molar concentration of products raised their appropriate powers ratio to product of molar concentrations of reactants raised to their appropriate powers which powers are got in a stoichiometric equation. Stoichiometric equation. And the equation should be reversed. The reaction should be reversed. The reversible reaction. What do I want you to emphasize? Product. Of molar concentrations of products raised to their appropriate powers, and it's a ratio, of course. Product of molar concentrations of reactants raised to their appropriate powers. Stoichiometric equation, reaction should be reversible. That is Kc, the concentration equilibrium constant. I talked of Kp. Kp is what we call the pressure equilibrium constant. Equilibrium constant expressed in terms of pressure. And this one occurs in or is written for reactions involving gases. Reactions involving gases. Because pressure exerted by solids is usually negligible, and that exerted by liquids is not often considered in chemical equilibrium. So for reactions involving gases, it's more convenient to express equilibrium constant in terms of Kp instead of Kc. And in the expression of Kp, we usually use what we call partial pressures. The partial pressures are usually in atmospheres in most cases. Let's look at an example, a reaction involving maybe X grams, and the reactant is X, not grams, okay? X gas is reacting with gas Y to give us a gas Z. If you balance this by A, B, and C, then the pressure equilibrium constant will be given as the partial pressure of the product which is Z, power C, divided by the partial pressure of X power A, multiplied by the partial pressure of Y to power B. That is the pressure equilibrium constant expression in terms of partial pressures. So somebody can ask you to define the pressure equilibrium constant. What will you say? It's the ratio of the product of the partial pressures of the products raised to their appropriate powers to the product of the partial pressures of the reactants raised to their appropriate powers from a stoichiometric equation at a given temperature for a reversible reaction at equilibrium. Thank you, my dears, for attending this session. Here comes an end. Subscribe to our YouTube channel for more of such. We meet next time where we shall see how to write expressions for equilibrium constants Kc or Kp using the law of mass action. I will introduce you to the relationship between Kp and Kc and then do experiments on chemical equilibrium. Bye-bye. Have a nice week.
Okay, teacher.